this question is on diffraction grating. So before proceeding to look at the question, let us see what a diffraction grating is. So a diffraction grating let me draw it. Diffraction grating is essentially basic n slits. So instead of double slit or 3 slits, we can consider diffraction grating to be a collection of n slits. So we have light will be, plane wave will be incident on the diffraction grating. So this is the grating. And then we will have the screen. So this is, let's say, the center. So at a given point P, waves from each of the contributing slits will interfere to give rise to a pattern. So diffraction grating can essentially be treated as n equally spaced slits of finite width. So unlike the double slit experiment in which we considered point-sized slits, in diffraction grating we will consider that these slits are having finite width. So diffraction grating is typically characterized by a parameter which is basically lines per inch or centimeter. So what does this tell us? This basically tells us that if we have a diffraction grating is made from a piece of glass in which either there are lines or grooves imprinted on it which block the light, and then there is transparent part which allows the passage of light. So passage of light would be through this transparent part, and then light will get blocked when it hits the lines. So this is a basic diagram of a diffraction grating. So let us consider the intensity pattern generated from such a grating. So as always, we will have, from here we will consider this angle to be theta. Now since each of these slits are having finite width, we saw in the case of single slit diffraction pattern for the case of finite width, since this grating is n equally spaced finite width slits, let us recap what we have for a single slit. So we had done it a few videos earlier, so I'll just copy it from here. So this was our case for single slit of finite width, single slit diffraction. This was the setup that we had. And finally, expression for electric field that we had is this one right here, where delta is the phase difference between the successive parts given as over here. So let me just copy these expressions. and paste it where we want it. So this is the electric field due to a single slit, where delta is given as such. Over here, this is our delta. So this is the case for a single slit. Now we have n such finite single slits in our grating. We have n of these. So this is slit 1, this is slit 2, slit 3, so on and so forth, n of such slits. So if we consider the phase difference between slit 1 and slit 2, so phase difference between consecutive slits, and if we call that equal to phi, so this phi will be obtained from let's say if you recall the double slit experiment. So in the double slit experiment, we had d sine theta as the path difference, so the corresponding phase difference will be 2 pi by lambda times d sine theta, which is equal to phi. So this comes from the double slit. So we are using both the concepts over here. We are using single slit, and we are also using the concept of double slit. So combining both these concepts of single slit and double slit to get the final expression for these n equally spaced slits. Before proceeding, let me clarify that b is the width of the slit and d is separation between slits. So this d is essentially equal to b plus the line width So as we said that this diffraction grating is basically some lines or some grooves made on a transparent glass material. So the width of this line, of these lines that we drew, let me draw in a different color. So the width of these lines plus the width of the transparent part, the slit. So this is the slit. So the green width is the slit width and the pink width is the line width. So sum of the slit width and the line width is the separation between two consecutive slits. So these are the parameters over here. Let us now come back to our expression for electric field. So electric field, total electric field due to n slits or the grating that we have. In such a case, the electric field at an angle theta at a given point P will be given as follows. It will be the electric field contribution due to a single slit. This is the single slit part. And then each of these single slits, successive slits, are having a phase difference of phi. So we have for the first slit S1, then between the first and the second slit is phi phase difference, between the first and the third slit is 2 phi, between the first and the fourth slit is 3 phi, so on and so forth up until the last slit, which is n phi phase difference. So let me just explain what these terms over here mean. So this is due to single slit part, and this comes from phase difference between the slits. So if you see this right here is from the first slit, so first slit is our S1. This is phase difference between S1 and S2. So let me just write between S1 and S2. This is between S1 and S3, and so on and so forth. So we have the field coming from S1. This is the single slit electric field amplitude. Phase difference is 0 for this one. This is our reference point. Then from S2 we have electric field coming in, which is having phi phase difference with respect to S1. So that's why we have e to the power I phi times the single slit part. Then for S3 the phase difference is 2 times phi with respect to our reference S1. So that's why we have e to the power 2I phi times the single slit part. So this is the expression. Now this is again a geometric series. This is a geometric series. With the first term equal to 1 and common ratio r is e to the power I phi. So sum of such a geometric series is given as follows. Sum of the n terms. So this gives us then finally this is our electric field expression. Now intensity is mod squared of the electric field. So this right here will be considering real amplitude for the field. Now in this term is the single slit intensity. So we can directly write this to be this, as we saw in the previous videos. This is some constant times sine squared alpha over alpha squared, where alpha is as follows. This we saw in one of the previous videos on single slit. For recap, we can check it once again. So here was the expression. This was single slit diffraction. This was the single slit diffraction pattern. Over here B was the slit width, and we found the electric field amplitude. Then we found out the intensity, and intensity came out to be as such: some constant times sine squared alpha over alpha squared, and alpha is pi b sine theta over lambda, b being the width of the slit and lambda being the wavelength. So we are using the same concept over here. Sorry, this n right here should be capital N. I've been using capital N. So let me rewrite it over here. Right, so this gives us our intensity is single slit part times the contribution from n such single slits. So let us write that. I'm opening these brackets. So this is what we get. This comes from the fact that e to the power I theta plus e to the power minus I theta is 2 cosine of theta. So further we can simplify it. So this comes from the fact that 1 minus cosine of theta is equal to 2 sine squared theta by 2. This is trigonometric identity. So finally we get the following. Now phi, we had written it earlier, is 2 pi d sine theta over lambda. So phi over 2 is pi d sine theta over lambda. Now let us call this a parameter beta. Beta is nothing but phi over 2. So let us come down. So this finally gives us, using beta equal to phi over 2, which is equal to pi d sine theta over lambda. So finally our final expression for intensity is as follows. Where, just to remind ourselves, I will write the parameters. where alpha is equal to pi b sine theta over lambda, beta is equal to pi d sine theta over lambda, b is slit width and d is separation between slits. So this is our final expression for the intensity on the screen. Now clearly separation between slits would be greater than the slit width, because separation between slit widths is slit width plus the line width. Now just for a schematic, if we draw the intensity pattern, so just as a schematic, so this is alpha, this is the single slit term sine squared alpha over alpha squared, so this is single slit. Then if we draw n slits, this is for the n slit part, this is beta, this axis, and this axis is sine squared n beta over sine squared beta. Now the diffraction grating is a product, so this is n slits, the diffraction grating pattern is a product of single slit of finite width and n slits of infinitesimal width. So taking a product, you will get n slits of finite width, so this is n slits point sized, and this is single slit finite width. So finally when you take the product, you will get n slits of finite width, and the pattern for that, if we take the product, is going to look somewhat like this. Let me draw. So we will have the envelope of the single slit, so this is the outline, the envelope for the single slit, and within this we will have the fringes of the n slit. So within this now we will have the n slit pattern, So this is the end slits modulated with the single slit envelope. Right, so this is single slit envelope. And this is the actual end slit finite width pattern, which is essentially equal to the grating pattern. So this basically was a discussion on grating and diffraction pattern from a grating. Now we can look at the question based on this diffraction grating that we have. So our question is, monochromatic light beam. So this is a helium neon laser of wavelength 632.8 nanometers is incident normally on a diffraction grating containing 6,000 grooves per centimeter. Find the angles at which the first and second order maxima are observed. What about the third order maxima? Do we find it? So this is our question. We have monochromatic light falling on a diffraction grating which has 600 grooves per centimeter, and we want to find out the location of first, second, and if possible the third maxima. So let us now solve the question. So 6,000 grooves per centimeter means that the spacing or separation between the slits D is 1 over 6,000 centimeter. So this comes out to be roughly 1.667 into 10 to the power minus 4 centimeter. So this is our separation between the slits. Now for maxima, the condition is d sine theta is equal to m lambda. So for first order maxima, m is equal to 1. We get the following. We get d sine theta for 1. First order is lambda. So sine theta for the first order is lambda over d. Lambda we are given is 632.8 nanometer. D we just found out is over here. This is 1667 nanometer approximately. So this gives us approximately 0.3796, which implies that theta 1 for the first order maximum is approximately 22.31 degrees. This is the first part of the question. Moving over to the second order maximum. We have the following. This is 2 lambda over d. So this comes out to be roughly and this gives us theta 2 as approximately 49.39 degrees. This is plugging into the calculator. Using the calculator to do the calculations, we get this. Now let us try and see what happens for the third order maximum. So third order maximum, for this m is equal to 3. Let us look at this carefully. So we have d sine theta 3 is equal to 3 lambda over d is sine theta 3. Now this comes out to be roughly 1.139, which is greater than 1. But we know that sine theta is bounded between -1 and +1. So this condition right here that we have got of sine theta being greater than 1, this is an invalid condition. So this is invalid condition or contradictory. This is impossible. So that means that we will not see the third order maximum. So this order maximum is impossible to observe. So that means we will only see first and second order maximum in this case. Beyond the second order maximum, we will not see any maxima because sine theta cannot exceed 1. So the number of maxima or the orders of maxima that we can see is essentially governed by this condition of d sine theta is equal to m lambda, such that sine theta is contained between -1 and +1. So if we write the condition, we have for maxima, we have d sine theta equal to m lambda, but sine theta is upper bounded by 1. So we have this needs to be less than or equal to 1. So this gives us that m is lesser than equal to d over lambda. So we are considering magnitude of sine theta is less than equal to 1. So magnitude of m is less than equal to d over lambda. So we can see only these many orders which are governed by the ratio d over lambda. Beyond this, we will not be able to see any order maximum. Just like in this example, we cannot see the third order maximum or higher order maxima. We can only see the first and the second order maxima. So this concludes the question. In this question, we saw the intensity pattern for a diffraction grating. We first saw what a diffraction grating is. Diffraction grating is essentially n equally spaced slits of finite width. Then we saw the intensity pattern of this, of the diffraction grating. So intensity pattern of the diffraction grating is essentially product of single slit finite width pattern product with the n slits pattern, in which each slit is infinitesimally small or point sized, and taking the product of the single slit and n slit, we get the diffraction pattern for the grating. And then we solved a question in which we realized that it is not possible to see all orders of maxima in a diffraction grating. The orders of maxima are limited by the d by lambda ratio.